All right, we're going to do lessons 13.6 and 13.7 all in one video because 13.7 is very short. So while I have your attention for 13.6, I'm just going to go ahead and finish it by doing 13.7 right after it. This is how I do it in class too. There is separate classwork for both of them. All right, 13.6 is about reaction mechanisms. Students will relate reaction rate to reaction mechanism. We can determine the rate law from the mechanism, and then we need to talk about what intermediates and catalysts are and how they are related to the mechanism. So here we have a balanced chemical equation and the experimentally determined rate law. We've done some sort of experiments like you've seen in lessons 13.2 or 13.3. We've been able to figure out what K is, what the order of the reaction is. There's the rate law. The balanced chemical equation, the 2H2 plus 2NO yields N2 plus 2H2O, does not show us the rate law. There's no relationship between the order of the reaction and the stoichiometry of the balanced chemical equation. It also doesn't show us the mechanism. It doesn't show us exactly how two hydrogen molecules and two NO molecules end up making a nitrogen and two waters. There's no way that all four of the molecules, two H2s and two NOs, all collide simultaneously, all four of those particles hitting at the same time, and boom, suddenly you have N2 and 2H2O. It's just not going to happen that way. It's too complicated. The chances of it occurring are too low. So something else must be going on. That's what the mechanism is what is that something else? What is the exact pathway that makes it happen? So a reaction mechanism is the series of elementary steps by which a reaction occurs. The elementary steps represent the reaction progress at a molecular level. What does each individual molecule do? How do the individual molecules collide? What do they create when just two molecules collide, for example? And the mechanisms are found experimentally, just like the rate laws. All of this is an experimental science. In fact, the rate law can help determine the mechanism. They kind of confirm each other. So here's an example. Using the same balanced chemical equation, the same rate law I just showed you. Let's say that someone has done the research to decide that the reaction mechanism occurs in two steps. There's the two steps. Let's add those up and we'll see that we get the balanced chemical equation, the overall equation. So add them together, you get this. I color-coded it so that you could easily see what's canceling out between those two steps. So it's the N2O that cancels out. What's up with that? It's called an intermediate species. A species produced in one elementary step and consumed in a subsequent step. Intermediate species do not appear in the balanced chemical equation, like the N2O just canceled out. The detection of an intermediate species during an experiment is evidence that the reaction mechanism may be correct. I'm underlining may be correct because there will never be proof. We'll never know for sure exactly how it happens. It's really, really hard to say exactly what each individual little molecule and atom are really doing. We can't really see that. We can't really control that. We're just trying to come up with a model the best we can. So if we can draw off some of the reaction mixture, for example, and analyze it, and we find, oh, look, N2O is existing in this mixture right now. Well, that's evidence that N2O is an intermediate, and it may help corroborate our mechanism. So how is an intermediate different from an activated complex, you may ask? Good question. Activated complex is all of the reactants of a particular step temporarily stuck together before the products are formed. It's not something that you can actually analyze for. It's really more of just an idea of how we're describing what's going to happen. Let's just say they all collide and stick together for a second. An intermediate is actually a product of a particular step. It exists, and then it undergoes another reaction and is changed into something else. An intermediate can be detected, can be measured. We can measure its concentration during the reaction. Activated complex cannot be detected. It doesn't exist long enough. So here is a potential energy diagram. You've seen these before, you've just never seen them with two hills like this. Usually we just show the reactants, the products, and one hill in between. And we say that that hill is the activation energy barrier that the reactants have to overcome to be able to form the products. Well, now we're showing two steps, two steps of the mechanism. We're showing both of those steps. Each hill is a separate step in the mechanism. Each hill has its own activation energy, EA and EA prime. And it shows you in between those two hills, the little valley right there, that's the potential energy of the intermediate that's formed. So you're going to want to be able to analyze this type of diagram as well and understand what the parts are and what they're telling you. So where are the activated complexes located on this diagram? Thinking back to when we first looked at the diagrams. They're right there where I just put the little stars. There's two activated complexes, one at the top of each little peak there. And which step do you think is slower, step 1 or step 2 of this mechanism, and why? Hopefully you said step 1 is slower because its activation energy is larger. Thus, its rate constant is smaller. So that's the type of question you might be asked about this diagram. So looking at that progress diagram a second ago, we could figure out which of the two steps in the multi-step reaction happens faster. We can say which elementary step is faster and which one's slower. That is important to us. We want to know why. We want to know which one's slower because we want to know which one is going to actually determine the overall rate of the reaction. That step is called the rate determining step. So we want to find out which elementary step is the rate determining step. So I have a demo that I usually do at school. Obviously, I can't do that right now. So I found a video that is someone who made the video to teach teachers how to do the demo. So I have the link for it here. I tried to play the video within this and just record that. Totally didn't work. So what you need to do is pause right now and go watch the video. I'm going to put this link in Schoology so you can just click it from there and not have to type all this stuff in. And I have the video starting at, you can see the end of this website, web link says T = 90. It means it's starting at 90 seconds in or a minute and a half in because blah, blah, blah. She talks a lot in the beginning. If you start from a minute and a half in, at least it gets you the important part of the demo. And so go watch that. You don't even have to watch the thing all the way till the end. If she starts getting boring again, you can just pause it and come back. So go do that and then come back and see me. All right, what you hopefully got out of that video is that the rate determining step, the slowest step in the mechanism, is the one that's going to control the overall rate of the reaction. So I got two funnels here. Obviously, one has a narrower opening than the other, a narrower spout than the other. So when the sand starts pouring through, it's going to get caught in the funnel with the narrower opening. So if I start pouring the sand into this, it's not going to accumulate in the first funnel. It's going to accumulate in this funnel because of the narrow opening. If I start pouring the sand in here, it's going to accumulate in this funnel and then come out in a narrow stream and go straight through here. It doesn't matter what order the funnels are in. The funnel with the narrower opening is the rate determining step. It doesn't matter what order the elementary steps come in. Whichever elementary step is the slowest is the one that controls the overall rate of the reaction. So when I do this in class, we actually time how long it takes for a certain amount of sand to flow through the funnels. Then we rearrange the funnels, we pour the same amount of sand through again, and we time it again. You get the same time either way to prove that it's all about the slowest funnel. That's all that matters. Okay, so in a multi-step reaction, the slowest step is the rate determining step. It's also called the rate limiting step. The overall reaction rate is the same as the rate for the slowest step. And the rate law can be determined from the stoichiometry of the rate determining step, but not from the stoichiometry of the overall reaction. We've already seen that. So here we are again with our reaction we were using earlier. And here are the two steps of the reaction, the two steps of the mechanism. We want to compare the experimentally determined rate law, which I have written right there, to the steps below and figure out which one of those two steps is the rate determining step. It's this one. Look at the stoichiometry of it. It says there's 1 mole of H2 and 2 moles of NO. Now look at the order of the reaction in the rate law. There is, it's an order of 1 for the H2, 2 for the NO. So what I'm saying is, let's see, pick a different color to draw with. Take this number right here, and it becomes that exponent. This 2 is that exponent. There's an invisible 1 right here. It is this exponent. That's what I'm saying is the connection. It only works for an elementary step, a rate determining step. You can't do it with the overall reaction because, for example, right here, this 2 in the overall reaction, I don't know why that won't write, is not showing up over here in the rate determining step. Molecularity of an elementary step is the number of molecules participating in the elementary step. That is the number of molecules colliding in the elementary step. Unimolecular, bimolecular, termolecular. I don't know why they don't call it trimolecular. It seems like it would make more sense, but they went with ter, so go with it. Unimolecular means the reactant molecule collides with solvent or spectators or even the walls of the container. It means one molecule is colliding with something and it's not colliding with another reactant molecule. Bimolecular means 2 reactant molecules collide. That is by far the most common. Termolecular means 3 molecules collide. That's fairly rare. I got this table out of, I think, Zoomdal, not Chang, so you're not going to find it in your textbook. So pause here and take the time to actually look at what it's saying. I'm not going to read the whole thing because that would be incredibly boring. But look at the elementary steps. Look at how they're categorized as unimolecular, bimolecular, or termolecular, and then look at how the rate law they've written relates to the elementary step that they've shown you. That's what you really need to be able to do, is relate the reactions that they're writing over here to this rate law. Figure out for yourself how they are the same, how they're related to each other. So get that out of your way so you can see. Pause here, take some time, think about it. Okay, why is termolecular uncommon and anything above ter is non-existent? So think about what termolecular is saying. It's saying 3 molecules, A, B, and C, all have to collide simultaneously, and they all have to collide in the correct orientation. Just think about the chances of that. They're very low. It just doesn't happen a lot. Now, if you're asking 4 molecules to collide simultaneously and all 4 of them be in exactly the right orientation, it's just not going to happen. So to prove a reaction mechanism, here's what you need. First, the elementary steps have to add up to the balanced chemical equation. That's easy. It's just like Hess's law. The rate law from the rate determining step must agree with the experimentally determined rate law. The reaction intermediates must be experimentally detected. So you have to be able to measure some concentration of an intermediate while the reaction's occurring. And why did I put the word prove in quotes? Because you're never really going to prove this. You're never going to know 100% for sure it's right. You're trying to develop a model of what's happening. You're basing your model on experimental data, just like every other model we've ever talked about. But are you ever going to prove that model is 100% true when it comes to looking at how molecules and atoms interact? No, you're not ever going to prove it. You're just coming up with a model and then supporting it as best you can with experimental results. Okay, here's another example. This is an example of like what you're actually expected to be able to do. So the overall balanced chemical equation and 2 steps of a mechanism are given to you. First of all, verify that the steps sum up to the overall equation. Add them up. What cancels out? Looks like the fluorines cancel out. Why does it cancel? It's an intermediate. Intermediate doesn't show up in the overall reaction. So you can verify that these 2 steps add up to the overall balanced chemical equation. Then, if you're told that the first step is slow and the second step is fast, they can ask you, what's the rate law? Use the stoichiometry of the slow step to write that rate law. Rate equals K, the rate constant, times concentration of NO2 times concentration of F2. It is first order in NO2. It is first order in F2 because the stoichiometric coefficients in the slow step are both 1. It's second order overall. Another example, new reaction. This one says, hold on, I gotta sneeze. It went away. Okay. All right, this one says that we have a slow step and we have a fast step that is in equilibrium. So again, if they tell us what the slow step is, we can write the rate law. Rate constant times first order in NOBr2 and first order in NO. It's the same information from the previous slide. I just printed it over again. So this rate law includes NOBr2, which is an intermediate. Look at the steps up there. See how it would cancel out? So it's very difficult to monitor the concentration of an intermediate while the reaction is occurring. So we really don't want to have our rate law based on the concentration of an intermediate. It's just not very practical. We'd like to find a way around that. Because the first reaction is in equilibrium, we can replace the concentration of NOBr2 in the rate law with the concentration of NO times the concentration of Br2. So here's what I'm trying to say. Let me get something to write with here. Pretend that it's kind of like algebra. Pretend that I'm replacing my equilibrium sign with an equal sign. I'm saying that this variable over here is equal to this plus this. Okay, I'm kind of saying they're equal. So I'm saying in the rate law, I don't really want this right here. So instead of putting that in there, I'm going to pretend that the concentration of NOBr2 equals the concentration of NO times the concentration of Br2. Everything here is raised to the first power because stoichiometrically everything is 1 mole. So instead of writing this part, I'm going to replace it with this new stuff right here. When I substitute that in, algebraically, I get this new rate law. Okay, that's how I remember it. I just think of it as variables and algebra. Okay, here's another example. Overall balanced chemical equation, got a new equation for you here, and I put I minus above the arrow. Why did I write it like that? What am I trying to tell you about I minus? What purpose does it serve in this reaction? Because I didn't write it as a reactant, I didn't write it as a product, so what am I trying to tell you it is? It's a catalyst. So here are 2 steps of a mechanism. I'm telling you which one's slow, which one's fast. Again, I ask you what the rate law is. You should be getting good at this because it's super easy. So for the slow reaction, I take the 2 reactants. They're both 1 mole each, so the stoichiometric coefficients become the order of the reaction. So here, I've included a catalyst in the rate law. That's okay. You can include a catalyst in the rate law. You don't need to try to substitute it out like you did with the intermediate. Catalysts speed up reactions by providing an alternate pathway, an alternate mechanism with a lower activation energy. So it makes sense that it's going to be involved in the rate law because it should be giving you a different rate because that catalyst is included. Also, you're controlling the concentration of the catalyst. You know exactly how much you're putting in there, so it's no problem to include that concentration in the rate law. You know what it is. So looking at my 2 reaction mechanism steps, just kind of reviewing stuff. Which species is the catalyst here? I minus. Which species is the intermediate here? IO minus. See how that would cancel out? Okay, so let's contrast catalysts versus intermediates to make sure you're seeing how they're different in the mechanism. Neither one is a reactant nor a product in the overall balanced chemical equation, but both appear in the elementary steps. An intermediate is formed in one step, consumed in a subsequent step. An intermediate appears as a product in one step and then a reactant in the subsequent step. Catalyst is consumed in one step, reformed in a subsequent step. It appears as a reactant in one step and then a product. So they're kind of opposites of each other in that way. All right, homework you're going to do is go read section 13.5 of Chang. It's going to give you more examples of mechanisms. This is one of these things where the more examples you see, the better you're going to get at analyzing them. There's so much variety. I cannot possibly show you all of them. Just go read them. Read through it. Read through all the examples in this section. Look at how they talk about getting the rate law from these mechanisms. And then some lovely classwork, which of course I will post key to. All right, let's do 13.7. I know this video is getting long. Just bear with me, I'm almost done. 13.7, catalysis. How do catalysts work? Classes of catalysts, examples of catalyst systems. All right, so how does a catalyst work? Works by stabilizing the activated complex and thus decreasing the activation energy, and/or providing an alternative reaction mechanism, a faster path from start to finish, possibly with lower activation energy. So when we showed the mechanism for the H2O2 decomposing and I- was the catalyst, we're saying that it's creating a new mechanism. It's creating a new series of elementary steps by putting that I- in there. So this is by far the explanation that I see used much more often than the other one. So this is probably the one I would focus on, alternate reaction mechanism. It gives you different elementary steps, and those steps are going to go faster. Remember that a catalyst is never consumed in the overall reaction. It's consumed in one step and then regenerated in another step. It changes the rate law, it changes the reaction mechanism, and it lowers the activation energy for both the forward and reverse reaction if you have a reaction in equilibrium. You've seen this type of drawing before. I know we did this first year. For the non-catalyzed reaction, the activation energy is higher, the hill is higher. For the catalyzed one, the activation energy has been reduced. But notice that the heat of the reaction and the potential energy of reactants and products are unaffected by the catalyst because the endpoints, the initial state and the final state, and delta H, all of that is a thermo concept, thermo and equilibrium. It has nothing to do with kinetics. The kinetic portion of this drawing is the only thing that's changing. So we've talked about this before as well. We said things like this is the kinetic portion as opposed to this is the thermo portion. Activation energy is a kinetic concept. Catalysts reduce the activation energy. They have no effect on those endpoints on the initial and final state. Delta H is a state function. It only matters what the initial and final state are. 3 classes of catalysts: heterogeneous, meaning in different phases. You can have a solid catalyst and a liquid or gas reaction mixture. Homogeneous or homogeneous, meaning they're all in the same phase. So your catalysts and your reactants are all liquids or all gases. And enzymes, biological catalysts found in the body, these are homogeneous and they'd be an aqueous solution. You're a great big aqueous solution. All right, you're going to go read Chang 13.6 to look at examples of catalyst systems. I listed 4 things here that you should definitely notice. The Haber process comes up a lot. You should have heard of it. Catalytic converters, those are in your car. Acid-base catalysis, enzyme catalysis. Just go read. You just need to be familiar with them. It's not like that they're expecting you to memorize all the details. It's more just if you've seen it before, when they bring it up again and ask you a question about catalysts, you're going to be able to answer it and not be freaked out by the fact you've never heard of the Haber process. And of course, there's some Bozeman videos. I've been listing those all along. There's more that relate specifically to this, and I will put links for all that on Schoology. And then lastly is the classwork. And again, I will put a key on Schoology for you.